Hello friends, welcome to PG department of LJ University. This is a lecture series of subject Applied Mathematics for the first semester student in Computer Engineering branch. Here I, Dharmin Patel, presenting a video lecture on the topic Eigenvalue and Eigenvector for 3x3 matrices. In the previous lecture, we already studied about the concept of eigenvalue and eigenvector, and also we discussed about how to find eigenvalues and eigenvectors for 2x2 matrices. In this lecture, we will discuss about how to find the eigenvalues and eigenvectors for 3x3 matrices. Let us start with our today's video lecture contents from unit number 1 linear algebra are eigenvalue eigenvector for 3x3 matrix, its characteristic equation, and some example related to eigenvalue eigenvector for 3x3 matrices. So let us start with the topics eigenvalue eigenvector for matrices 3x3 matrices and characteristic equation of this 3x3 matrices. So first of all, we will see what is eigenvalue eigenvector. Already we know about the concept of eigenvalue and eigenvector, which is similar to this. Here A be a 3x3 matrix and x bar is any vector in R cube and it is a non-zero vector. If it is an eigenvector, then we can rewrite this matrix multiplication Ax bar is equal to matrix A into column vector xyz equal to some resulting matrix KLM, and it is a new vector in R cube. But when x bar is an eigenvector and Ax bar equal to lambda x bar, then A lambda is called eigenvalue and x bar is our eigenvector for matrix A. In this case, we can rewrite Ax bar equal to lambda I x bar, and that can be written as in the homogeneous system form A minus lambda I x bar equal to 0. That is our homogeneous system of linear equation, and we want to find and we want to find here the non-trivial solution of homogeneous system linear equation 1. So we are taking determinant of A minus lambda I equal to 0. If we are taking the determinant of A minus lambda I is equal to 0, not equal to 0, then we have a trivial solution which is x bar equal to 0, which is not possible because we already assumed that x bar is not equal to 0. Now we have a determinant of A minus lambda I equal to 0, then it is a characteristic equation of 3x3 matrix A minus lambda equal to 0, that can be rewrite as lambda cube minus S1 lambda square plus S2 lambda minus S3 equal to 0. Here A is our matrix and S1 is a trace of matrix, that is the sum of diagonal elements. So here A11 plus A22 plus A33 is a trace of matrix for our matrix A, and S2 be a sum of minors of diagonal elements and S2 be a sum of minors of diagonal elements. And here first determinant represent the minors of A11, second determinant represent the minors of A22 element, and the third determinant represent the minor of A33 element, and S3 is a determinant of whole matrix A. So that is the characteristic equation for 3x3 matrix only. And after solving this characteristic equation, we get the maximum 3 different values of lambda, and it is called the eigenvalues for 3x3 matrix. Now we will see the examples of eigenvalue and eigenvector for 3x3 matrices. Here we have a matrix 1 1 0 1 0 1 and 0 1 1. It is a 3x3 matrix of order 3 by 3, and first of all we will find the eigenvalues and then we will find eigenvectors. So here X bar is our eigenvector and it is a non-zero eigenvector in R cube, and A is our matrix, x bar is not equal to 0. Now we can rewrite Ax bar equal to lambda x bar, that can be A minus lambda Ax bar equal to 0, which is our homogeneous system of linear equation. For this matrix, it can be rewrite this type, and now we can see that in the diagonal we have a 1 minus lambda, 0 minus lambda and 1 minus lambda. Other entries are as it is. This is a homogeneous system of linear equation, and we are interested to find the non-trivial solution for this homogeneous system of linear equation. So finally we have a determinant of A minus lambda equal to 0. So we can rewrite our characteristic equation as lambda cube minus s1 lambda square plus s2 lambda minus s3 equal to 0. Here we know that s1 is a trace of matrix A. So here S1 is trace of A, that is A11 plus A22 plus A33, so it is a 2 according to our matrix, and S2 is a sum of minors of diagonal elements. Here first determinant is our 1 minus 1, second determinant is 1, and third determinant is minus 1. So finally our S2 is minus 1, and determinant of this matrix is S3 is equal to minus 2. So our characteristic equation is look like this, and now we properly write as lambda cube minus 2 lambda square minus lambda plus 2 equal to 0. Now we can easily factorize this particular characteristic equation, and we get the factors as below: lambda square minus 1 minus lambda 2 equal to 0. So we have a lambda minus 1, lambda minus plus 1 and lambda minus 2 equal to 0. So our eigenvalues are 1, minus 1 and 2. Now next target is how to find the eigenvectors for 3 cross 3 matrices. So now we will see the eigenvectors for eigenvalue lambda 1 equal to 1. So here we will take the lambda 1 equal to 1 in place of lambda. Now we are interested to find the eigenvector for lambda 1 equal to 1. Here every time we will find the eigenvector corresponding to each eigenvalue individually. So here we are finding the eigenvector for lambda 1 equal to 1. First of all, we replace the homogeneous system by lambda equal to lambda 1. So here our system is look like this: A minus lambda 1 I x bar equal to 0 vector, and we after putting the lambda 1 equal to 1 we get this type of homogeneous system. In this system we can see that first row and second last row are equal. So we are applying here Cramer's rule, and we consider any two lines. Here we consider any two different row from this matrix. So here we are applying the Cramer's rule for finding the eigenvectors. So we are taking the second and third row. You can also take the first and second row, but you can't take first and last row. So finally here after taking the this particular two rows, we get the x upon first determinant, second determinant, third determinant. So here after applying the Cramer's rule, now by Cramer rule we have a x upon this determinant minus 1, 1, 0, 1, after taking minus y upon 1, 1, 0, 0 and z upon 1, minus 1, 0, 1. So that is our Cramer's rule. Here we solve this particular relation between x, y, z in the terms of t. So finally we have this type of situation: x equal to minus t, y equal to. We have solved this relation in terms of t, and then we have a solution like this: x equal to minus t, y equal to 0 and z equal to t. After taking t equal to 1, we have a minus 1, 0, 1, which is our eigenvector for lambda 1 equal to 1. So similarly, after applying the Cramer's rule for lambda equal to 1, we have this corresponding eigenvector. For lambda equal to 2, we have this eigenvector, and lambda equal to 3, we have this eigenvectors. So these are the linearly independent eigenvectors for 3 cross 3 matrices. So this is the concept of finding eigenvalues and eigenvectors for the 3 cross 3 matrices. And now already here we studied the concept of eigenvalue eigenvector for 3 cross 3 matrices, how to find the characteristic equation, and some examples related to 3 cross 3 matrices for eigenvalue and eigenvector. And in the next lecture we will discuss about the diagonalization of matrices and the Cayley-Hamilton theorem for eigenvalues and eigenvectors. Thank you very much.